Hello everyone, welcome to the first lecture of week 10 of the course Power Network Analysis, in which we continue our discussion on fault analysis. And in the previous lecture, we extensively talk about the importance or application of Thevenin's theorem in fault analysis. We also talked about certain assumptions that would help simplify our analysis and keep the computational burden to the least minimum possible while finding out the worst case fault currents. And in today's discussion, we will take up the application of Thevenin's theorem to understand in detail how balanced faults, three-phase faults, can be analyzed in a very unique, beautiful, simpler fashion. So what we have here is a usual n-burst network. We have also seen this sort of a network while we were discussing power flow analysis. So I have in fact taken up the same diagram from the power flow analysis module. And what we have here is a n-burst network where buses are numbered from bus 1 to bus 2 till bus n. And this power network which I have considered, n-bus power network, it is operating in a balanced condition. We have talked about balanced and unbalanced a bit in basic circuit principles. Those of you who are eager to know more, they can refer to those particular basic circuit principles lectures. Or you can wait till the next lecture where in detail we will also have extensively discussion on what is balanced and unbalanced. So essentially I am assuming that this n-bus network is balanced, is operating in a balanced condition. That means all voltage phasors of the three phases, they are equal in magnitude, and the corresponding phase angle difference between these voltage phasors, they are 120-degree apart. Same logic also holds true for the three-phase currents, could be in phase domain or line to line. So important part is that this n-bus network is operating in a balanced condition, and hence the single line or per unit based representation is applicable for this n-bus network, where instead of representing the three phases separately, just a single phase representation on per unit basis is good enough to represent the actual three-phase balanced network. So with this as our premise, we have a n-bus network which is balanced, can be represented by a single phase representation, and before the fault has occurred or before any disturbance has occurred, we know for sure what are these equivalent single phase per unit equivalent balanced voltages or single phase voltages at each of the buses 1 to capital N. And we choose bus K to be our, so essentially these arrows here, they are indicating the presence of any source or load which might be present in these, on each of these n-bus networks. Depending on whether the source is present, the injection is going to be positive, so this arrow is applicable. If there is a load present, again a rotating load specifically, then the arrow direction would change because the corresponding injection would be negative. So we are not so very bothered about what these injections are as of now, but we know that, okay, in the pre-fault condition before the fault has occurred, the pre-fault voltages, they are all known at all the buses. And we choose bus K as our bus where a fault is likely to occur, and we call that fault to be a three-phase fault. Since the network is balanced in the pre-fault condition and now a three-phase fault is occurring at bus K, how it would occur? If this switch is closed, then it would indicate that bus K is grounded. Basically, so this is the ground connection. By closing the switch, it would imply that bus K is now grounded through a fault impedance ZF. And since this is a per unit based representation of a three-phase network, balanced three-phase network, on three-phase basis, it would appear that all the three phases, phase A, phase B, phase C of bus K, which are VAK, VBK and VCK in phasor domain, in time domain or respective phasor domain, all the three buses are equivalently, all the three phases of the same bus are equally connected to the ground through this common fault impedance ZF. Since we are talking about a balanced network, balanced fault, so we have considered the single phase representation of this fault impedance ZF, and this three-phase fault is going to occur by closure of this switch. So basically our points of interest are bus K itself and the ground, in which a new event is going to happen compared to the pre-fault condition where everything was perfectly fine. To analyze the impact of this fault, we will have to find the corresponding Thevenin equivalent circuit between bus K and the ground, because it is these two nodes or points between which this three-phase fault is going to occur. So essentially we have to find the Thevenin circuit of the actual power network as seen from the 2 points of reference, one bus K and the other being ground Z, the ground point itself. So question here is that, okay, Thevenin circuit has to be found so that Thevenin's theorem could be applied to understand the implication of this three-phase fault. So the point of interest is, how do we find this Thevenin circuit, or before we apply Thevenin's theorem, how do we find the corresponding Thevenin circuit? For time being, we will assume that by some analysis, okay, we are able to find that Thevenin's theorem, and while finding the Thevenin's theorem, which would consist of the Thevenin voltage and the Thevenin impedance, while finding Thevenin impedance, it is important to represent all rotating devices, synchronous generators, induction motors, synchronous motors, by their respective direct axis transient reactances. So in addition to considering the N-bus network, which is highly meshed, this circle here basically means that this N-bus network is highly meshed. The lot of lines exist inside this encircled network. Or while finding the Thevenin impedance ZTH, we have to consider all network line impedances. Basically, if we ignore the shunt susceptance and resistance, we'll have to consider all line reactances. We'll have to consider transformer reactances, which are part of the power network itself. And also we have to consider the direct axis subtransient reactances of the rotating machines. That is an important aspect. And while finding Thevenin circuit, we have to be careful in shorting all voltage sources with generators being represented by the direct axis subtransient reactances. So this part needs to be considered carefully. We'll also understand this aspect while we discuss a numeric example towards the end of this lecture. So suppose by some analysis, we don't know for sure what that analysis is of how to find ZTH and how to find VTH. Suppose we get to know that VTH and ZTH which pertain to the pre-fault condition of the network. Remember, for analyzing or applying Thevenin's theorem, in fact in the previous lecture also, Thevenin circuit is always to be found in the pre-fault condition before the switch was closed. Now once you find the Thevenin's theorem, you get to know what is VTH, ZTH. We don't know for sure what those values are, but now you can apply Thevenin's theorem and superimpose the fault event where now the switch is closed. So now when the switch is closed, a current would likely flow from the ground, from the bus to the ground, and the implication or direction of this fault current is important. We'll spend a moment here to understand why the fault current has to flow from the bus to the ground, or for that matter, why VTH polarity is of this particular order. The positive polarity is connected to the ground. Suppose VTH polarity was to be plus and minus compared to minus and plus shown over here, then what would happen? Instead of IF flowing downwards from bus K to ground, current would flow from ground to the bus, which would mean that, okay, fine, that if this phenomena were to happen, that means if VTH were to be of polarity plus minus as shown above, then in that case the current would flow from the ground to bus K, which would be a win-win condition for the power network, because without doing anything, we are able to get new additional source of current, which is the ground in this case, and this ground is capable of supplying our loads. Does it sound practical? Definitely no. That's the reason why this sort of polarity is not at all applicable. It is a fault which has occurred. It should not, I mean, a fault is anything that interrupts the flow of normal load current. If the polarity is now reversed from minus plus to plus minus, the fault would help supplying loads, and we would be able to cater to loads without generating anything new, and that definitely is not possible. So that's the reason why VTH polarity is such that during a fault, current is drawn from the network to the ground, which otherwise could have gone to some useful load if this fault would not have occurred. That's the reason why VTH is of the polarity shown like this, so that the current is flowing into the ground from the actual network. So with this new current that is going to flow, it is definitely going to bring in few change in voltages. Again, our question mark points are, what is this VTH, what is this ZTH? Only when we know VTH, ZTH, then only we can know what is IF. So suppose we know VTH, ZTH, and this fault has occurred. So fault current is being drawn from the network to the ground, and because of this fault current, the voltages on the buses might have changed. Let us indicate those changes by this vector delta V, which is of the same dimension n cross 1 as a V pre, which was the pre-fault voltage. By Thevenin's theorem, if we can know what are these delta V values, then we can apply superposition theorem and get to know our post-fault voltages, which would be superimposition of pre-fault voltage and the change in voltages. This change in voltages, it is dependent upon the Z-bus matrix, which was obtained from Y-bus, which is inverse, and a current injection vector, which is again a n cross 1 matrix. Remember, this Y-bus needs to be evaluated while considering the generator's direct axis subtransient reactances along with other network impedances, transformer reactances, etc., etc. So now, if we get to know what is delta I, because Z-bus can be known from Y-bus inverse, then only we can know what is delta V. Now, if we think about what is delta I, which is essentially, what is delta I? Delta I is change in bus injection currents due to three-phase fault between bus K and ground. This is basically going to be a n cross 1 vector, which is essentially encapsulating all change in currents that are going to happen because of the three-phase fault which has occurred between bus K and ground. Now, if we think for a moment, delta I is a n cross 1 vector. So, this is essentially equal to delta I1, delta I2, all the way till delta Ik, and the last element is delta I capital N. We want to find what is this delta I vector. If we know delta I, we can find delta V, and possibly we know already pre-fault voltage V pre, so we can find V post, and then our purpose would be done. Now, if we think for a moment, what is going to be delta I? Do you think delta I1 is going to be 0 or non-zero? Okay, let's see. Delta I1 is change in current at bus 1 due to fault between bus K and ground. If the fault has occurred between bus K and ground and a current IF is flowing from bus K to ground, why should current in bus 1 change at all? The scenario has not changed on bus 1 in itself actually. At least directly speaking, bus 1 current has not encountered any change at all. It is only bus K which is experiencing this change in fault current, which is IF, which again depends on what is VTH and ZTH. So why should bus 1 current change? And that's the reason why all currents, they would be exactly equal to 0 except delta Ik. Now remember, when we defined bus injection currents, we inherently assume these injection currents to be currents flowing from the bus into the network. During a fault, current would flow from the network to the ground. That means delta Ik imperatively, which would mean any injection which is happening from the bus to the network. In case of fault, delta Ik is equal to minus delta IF, because IF is flowing from the network to the ground. So this current is actually being drawn from the network to the bus, and that's the reason why we have a negative sign here. The directions or notions are different. So delta ik is the only non-zero element present in delta I vector, as all other generators are unaffected, they are shorted. All generators are represented by their internal EMFs and corresponding direct axis reactances. While finding Thevenin impedances, we are considering all voltage sources to be shorted. So all other voltage sources, they are null and void. Their voltage sources don't play any role in the overall Thevenin circuit that we are going to look at. So all other generators, they are shorted, and hence all other currents, bus currents, they are zero. Only delta Ik is the non-zero current. Now if we sort of substitute this delta Ik non-zero element, which is minus delta IF at the kth position sitting over here, this is the kth element of delta I, and put in our V post voltage, which is n cross 1 vector in terms of n cross 1 pre-fault voltage and the n cross n Z bus matrix that we have. What we would see is that all post-fault voltages, they would only depend on the actual pre-fault voltages and the kth row of Z bus matrix, because since all currents here are zero except for the kth element, so these elements, their contributions won't come. All post-fault voltages would only depend on the kth row of Z bus and the corresponding IF value which has happened or change has happened on the bus K. So if we look at bus K equation, then Vk post would be equal to Vk pre plus Zik into minus delta IF, because all other elements, pardon me, I made a mistake here. Instead of the post-fault voltages depending only on the kth row of Z bus, they would actually depend on the kth column of Z bus, because only the kth element of delta I is non-zero. So if we look at bus K equation, then and focus on the kth column of Z bus, only Zkk term is appearing here, which is in product with minus IF. So we have Vk post as this equation. Also, as per this circuit here, if the fault has now happened, the switch is now closed, the voltage of bus K is Vk post itself, and by KVL between bus K and ground, Vk post is nothing but IF into ZF. That means this term has to be equal to IF into ZF, because post-fault voltage at bus K is the voltage after the switch is closed. So this new bus voltage is Vk post. And from here, if we sort of, from this equation, if we compare, IF should be equal to Vk pre divided by Zkk plus Zf. That is one equation that we get, because after the voltage of fault has occurred, the post-fault voltage by KVL should be IF ZF, and by Thevenin's theorem it should be pre-fault voltage plus the change in voltage that might have occurred. If we compare the IF current with respect to KVL shown over here, then IF is also equal to VTH by ZTH plus ZF. Now compare these two equations that we get. This is the equation that we are getting by KVL from ground to ground. Vk post is equal to IF ZF by applying KVL between bus K and ground. If we compare these two equations, we see a great lot of similarity. The similarity is that the Thevenin voltage happens to be same as the pre-fault voltage, which is Vk pre, and Thevenin impedance is nothing but k, kth element of the Z bus matrix. And remember, in Thevenin's theorem application, we always focus on the pre-fault condition. We don't consider the impact of fault yet while evaluating the Thevenin circuit. And by comparison of elements, what we see here is that the Thevenin circuit that we are getting in terms of Thevenin voltage and Thevenin impedance, they also happen to be the pre-fault situation, not the post-fault situation. And that is where Vk pre is important. Zkk is k, k element of Z bus matrix, which was evaluated from Y bus inverse, where Y bus was obtained by considering all voltage sources to be shorted, with generator, subtransient reactances and other network elements only being present. So that's the logic or sort of reverse engineering process of obtaining or finding a Thevenin voltage and Thevenin impedance. Once you know Thevenin voltage, Thevenin impedance, you can find the fault current. Once you know the fault current, you can evaluate your delta I vector. Once you know delta I, you can find delta V. Superimpose delta V, this entire element on V pre to find the new post-fault voltages. And essentially, once you know the post-fault voltages in three-phase fault, you can find the corresponding fault currents and all necessary evaluations that you need. These are the expressions for post-fault voltages. These are the expressions for post-fault currents in three-phase faults. Remember here, small Zij is not the I comma j element of Y bus or Z bus. It is the actual line impedance between buses I and J. So once you know the post-fault voltages, post-fault currents, your analysis is all done and complete. And the above current line expression can also be used to find the corresponding phase currents. Since we are talking about balanced fault, so the single line per unit representation of current that you would get, the same can be extended to all the three phases. Before we go into the example for today's discussion, there is another important aspect or notion defined as short circuit capacity, which indicates that at a given bus in a power network, what is the maximum amount of power that can be exchanged or that can flow in case a dead short circuit three-phase fault occurs in the network. So essentially, the three-phase faults, they are the most severe faults, and if they happen to be bolted faults where fault dependence is zero, you can imagine the fault current would be as high as possible. One simple example or indication here is that if ZF tends to be zero, the denominator would tend to go down, the corresponding numerator would go up. So for bolted three-phase faults, fault currents would be severe, and short circuit capacity, in short known as SCC, is the estimation of what is the maximum amount of power that would flow during a fault condition. So in terms of three-phase line-to-line pre-fault voltage and short circuit current ISC, which we have evaluated as IF in the previous few lecture slides, in terms of per unit, this is the actual SCC value if we divided it by the rated base power of the given network, where VLL mostly happens to be same both for pre-fault and post-fault conditions. The difference is not much. Then in that case, SCC in per unit can be equalized to be equal to inverse of the Thevenin impedance. Now, why we are ignoring the presence of ZF? Because if we ignore the presence of ZF, SCC will still give us a worst possible value. So, we are going for the most pessimistic or worst case condition. And the rating of in terms of SCC that we get for every such bus in a given network dictates what is going to be the rating or breaking capacity of the associated circuit breaker and isolator. Because if these breakers and isolators cannot handle such high currents or high quantum of power flow, they themselves would be at stake, and hence overall system protection, which would help protecting the network from these disastrous faults, would be at stake. So the devices that are useful for protecting the power network, they should be capable of withstanding or withholding their operation under such high SCC values, and that's where the importance of short circuit capacity comes into picture. We'll conclude our discussion today with an example. The problem statement looks very long, but don't worry, I'll simply summarize it in the least possible fashion. What we have here is a three-bus network in which bus 1 and bus 2 have generators connected to them through three-phase transformers, star grounded on bus 1, and delta and star grounded on bus 2. The generators neutral points, they are also grounded, which is indicated by this star grounded connection. They are also neutrally grounded through certain reactance or impedance, which for the problem at statement is not important. We don't have to bother about what this reactance values are as of now for three-phase faults. It would become important when we discuss about unbalanced faults. These generators which are there at bus 1 and bus 2, they have their respective behind the subtransient reactance, not the transient reactance. The subtransient reactances of respective generators are given as J.1 pu, J.2 pu. The transformers reactances are also given as J.1 and J.2 pu. All resistances, susceptances, capacitances are all neglected so that our analysis can become simpler and we can find the worst possible conditions of currents. Line which are present between bus 1, 2 and 3, their reactances are also given in terms of per unit. The question here is that during a no load pre-fault condition, because generators are at no load, they are running at their rated voltages with rated frequencies so that the EMFs are all in phase. We have to find the fault current, bus voltage, line currents, etc., etc. during a balanced fault at bus 3 through a fault impedance of ZF equal to 0.16 pu. Okay, that's what we have to find, that in case this switch gets closed, then what would be the currents through these lines, what is the contribution to the generators and corresponding voltages and so on. So what do? We have to apply Thevenin's theorem, but before we apply Thevenin's theorem, let us take certain relevant information from the statement which has been given. The generators, they are represented by a EMF behind the subtransient reactance, that is information number 1. Information number 2, the system is at no load, that is point number 2. Information number 3, all generators are running at the rated voltage with rated frequency so that the EMFs are all in phase. That means if I have to redraw this circuit, which is the one which I'll try to draw over here, then I have E1, which is 1 at an angle 0 per unit. This is in series with its subtransient reactance XD equal to J.1, then followed by the reactance of the transformer J.1, and then I have bus 1 present over here. Similarly, for bus 2, if I draw, I have an internal EMF E2, which is the value, I'll mention that in a moment. Then I have XD of the generator 2, which is J.2, and XT, the second transformer, which is again of reactance J.2 per unit. What do you guess should be the value of E2? E2, as per statements 1, 2 and 3, the EMFs are at rated voltage. The rated voltage is on a common base going to be 1 pu. The EMFs are also in phase. That means E2 is 1 because its voltage is rated voltage. Since they are in phase, the angle here also is 0 degrees, if I am choosing 0 degrees as a reference. And since 1 at an angle 0 degrees is the per unit voltage of the internal EMF, the same if I have to imply, because as per point number 2, there is no load in the network. That means these currents, they don't exist because there is no load actually happening. For no current to flow, all my buses, bus number 1, bus number 2, they would also be at the same unique potential in the pre-fault condition. 1 are 2 connected by 0.8, and similarly 1 and 3 and 2 and 3 are connected by J.4, 0.4 equivalently, and bus 3 also has a pre-fault voltage of 1 at an angle 0. In case these pre-fault voltages differ, currents would flow which would violate the condition that the system was at no load. If the system was loaded, these currents would have been different, the voltages would not have been unique. So we can safely assume that whatever voltage we have to measure in the pre-fault condition, they are all 1 at an angle 0 degrees. 0 being an arbitrary choice for reference, you could choose any other value also, although 0 degrees or 0 radian makes our life simpler. So with this as our pre-fault condition, we now apply Thevenin's theorem to understand what would be the implication of this three-phase short circuit fault. So let's do that. So this three-phase short circuit fault, it can be analyzed by Thevenin's theorem. So this Thevenin voltage at bus 3 with respect to ground is V30, which is the same value of 1 at an angle 0 degree because it's a pre-fault condition. So Thevenin voltage can be known. To find the Thevenin impedance between bus 3 and bus K, the points across which the disturbance or fault has occurred, we can simplify this circuit, apply combinations of equivalent resistances, impedances, do delta star star delta conversion, so that this essentially figure B here is redrawn as figure A with delta star conversion applied. And here we see that between S and ground, there are two similar paths. One path has J.4 impedance. The other part has J 0.6 impedance, which together when equivalently parallelly obtained would result in J 0.4 impedance. And now S and 3, they are J1 connected, and this goes on. So if we combine J 0.424 and 0.1, we get Z33 as 0.34 J, which is the one which is shown over here. So this is all possible to do when the network is smaller. Imagine if it would have been a 300 bus network where at some bus this particular fault occurs. Would it be possible to go into all these star delta convergence, parallel convergence? Practically not possible. It's practically possible but not feasible to do, in the sense the meshes would be enormously high and one would get lost. So is there any other way of finding Thevenin impedance? Yes, that's where the term Z33 comes into picture. Let us now try to find the Y bus matrix, Z bus matrix, and see whether the third element of Z bus turns out to be J 0.34. Let's do that. So in the pre-fault condition, while applying Thevenin's theorem, we have to be careful about the pre-fault admittance part only, and our generators, they are all represented by their internal reactances. Transformer reactances are also there. So that's the reason if I combine these two together, it becomes J 0.2 as shown over here. And similarly for the other generator, it is becoming J 0.4, J 0.2 being its own internal reactance, the transient reactance, and J 0.2 is the transformer's reactance. So if I combine these two reactances and apply my simple Y bus evaluation, I'll first try to find my admittances. So Y10, Y20, 0 here refers to the ground. Y10 is J 0.2 inverse, Y20, Y13, 23, and so on, the same usual process. From there I find my Y bus, take the inverse of it, I'll get my Z bus. Here the third element is the same number which I had obtained by doing my manual evaluations of star delta delta star convergence. So what I'm trying to say is, to find Thevenin impedance, please find Y bus of the network, take its inverse. Don't go into impedance evaluation, combination, parallel combination. No, it's going to be a rigorous process. The simpler exercise is to find the Y bus, keeping in view that the generators are marked by their internal subtransient reactances, and find the corresponding Y bus, take the inverse, you will directly get the Thevenin impedance. So once we know the Thevenin impedance, our pre-fault voltage, they are all 1 at an angle 0. I think I have missed that part here. Yes, it was given over here. And I have also discussed that in slide number 11. So once my pre-fault voltage is known, I can find the fault current. I3F is minus J2 PU. The question was to find the fault current, which we have now found. Can we find the generator's contribution? Yes. There can be two ways of finding the generator contribution. One simpler way is, if this IF has to be J2 PU, that means the current through S and 3 should also be J2 PU. That means the current IG1 and IG2, they should together contribute and add up to J2 PU. Now how do I find IG1, IG2? There are two parallel paths between S and the zero ground. So the currents would distribute in themselves as per the inverse ratio of their respective impedances, and that's the reason while finding J1, I consider J 0.2 and 0.4, which add up to 0.6, which gives me a current contribution of minus J 1.2 PU, and correspondingly generator's 2 contribution is minus J 0.8 PU. Together they add up to minus J2 PU, which is the fault current. Once I know my generator currents, I can also know what are my change in injection currents delta I. From there I can find the change in voltages delta V1, delta V2, delta V3, superimpose them on the pre-fault voltages, which are all 1, 1 and 1, and find the actual voltages after the fault. Once I know my actual voltages, I can find the corresponding fault currents after the fault has occurred in terms of the lines I12, I13 and 23, which are differences across the voltages of different buses divided by their actual line impedances. So remember, Z12 is J 0.8. This is not equal to 1, 2 element of Z bus. Please be careful in that sense. It is not the 1, 2th element of Z bus. It is the actual line impedance. So what I observe here is that J12 current is J 0.1 PU, which means I21 would be J 0.1. I13 is J 1.1 PU, I23 is J 0.9 PU, and after the switch is closed, IF is J2PU itself, minus J2PU. So if I apply KCL at node 3, is my KCL applicable? Yes. Minus J.1 added with minus J.9 adds up to minus J2PU. Is the KCL applicable at bus 1? Remember, bus 1 generator current was minus J1.2, generator 2 current was minus J.8. So basically this is the current flowing from the ground to bus 1 during the event of a fault, which is minus J.8, and minus J.1 added with minus J.1 adds up to J.2. So KCL here is also true. Similarly, KCL here is also true. Now the only part which is left is to explain is how is minus J1.2 current flowing over bus from the ground to bus 1, where the post fault voltage at bus 1 is 0.76 pu. That means, is the KVL applied over here? Probably no. Is there something missing? Yes. The part which I am missing here is that I have not considered the internal EMF of the generator before this grounding point. This internal generator E1 was 1 at an angle pu. Now if I consider the internal EMF considered together, E2, which is also 1 at an angle 0 pu, 1 minus 0.76 is 0.24. 0.24 divided by J.2 gives me minus J1.2 current. So be careful in finding generator currents. That's the other alternative of finding generator currents. You need not always do current division as shown over here. You can avoid this step entirely. Find the post-fault voltages, find the actual voltages, go back to the pre-fault circuit where generators were marked by their internal EMFs as shown over here. Now V1 instead of being 1 at an angle 0 pu is 0.76 pu. Apply KVL between these two nodes E1 and bus 1, you would find minus J1.2 as the actual fault current. Same goes with E2 and bus 2. So that's the entire logic. You can actually sort of avoid these combinations of resistances. Try finding Thevenin impedance through Z bus and Y bus. Also can avoid generator contribution evaluation through this current division manner and actually evaluate them from the actual post-fault voltages. With this, I conclude today's discussion. In the next lecture, we will talk about Fortescue's theorem and its application for unbalanced networks and sequence components. Thank you.